Hi guys, is there anyone here? I'll just get started now. Okay, so this is the Data Structures II Editorial. Sorry for the wait, but yes. For question 1, merge sets, is the hard part is basically trying to read the question, but yeah, basically what they're basically the important thing to note here is that because your A can be up to 10 to the power of 9, so it won't fit in like a regular array. So you basically need to discretize the value of A. So just because even though like A can technically go up to 10 to the power of 9, because of the other limitations in the questions, it's not actually going to take up all the space, like all 10 to the power of 9 possible values. So if we try to like store it in an array, you actually can't create an array of size 10 to the power of 9, because it's just going to crash your computer, because you're using up way too much memory. So instead we have to use a hash table. We have to use a hash table to basically discretize our arrays, so to like in a way compress it down, so that to like basically make sure that we are not wasting our memory trying to store something that isn't actually being used. So yeah, and you also need like lightning rod IO to pass this question. Yeah, so like this, like in a nutshell, this question is quite scam. Right, for question 2, box in box, the important like observation to note here is that since we can rotate the box in like any way we want, we can just sort the height, width, and the depth, so that the height is always less than the width, it's always less than or equals to the depth, so because you can rotate the boxes, so that it means that you can essentially just do this. So once we've sorted our values, it's going to make calculating it much easier. So after this, we just process the boxes in increasing height. So we need to check if there's for a box HI that we are looking at right now, if we need to check if there's a box J such that the width of J is less than the width of our current box, and the depth of our new box is also less than our depth of our current box. And because J is less than I, because we are sorting the box by their heights, since J is less than I, we can basically be sure that the height of this new box is less than the one of our current box. So we use a segment tree to keep track of the boxes where the index is W, and the value where the index is basically the width and the value is the depth. So basically for each box, we're just going to query the minimum depth from 1 all the way to width minus 1, and then check if it's less than the depth of our current box that we're checking. So but the problem is if the heights of the two boxes are equal, then we just use a tie break by descending W, so that it's because since the heights are equal, it can't be put, you can't put it within each, you can't put it inside each other. So we'll just have to tie break by descending W and not count this box. Yes, but but similarly to question 1, there's also a problem because see in the questions, the height, the width, and the depth can go up to 10 to the power of 9. So either you're going to have to use a lazy create segment tree, or you're going to have to discretize the value. So I'm going to show you how a lazy create segment tree works. Okay, let me switch my screens first. Alright, so basically this is our lazy create segment tree. So the idea behind a lazy create segment tree is that since you're not going to need all the values, so even though you're not, because there's up to 10 to the power of 9 values, if you try to just create all the nodes like we showed you in the data structures 2 lecture on segment trees, if you remember from that lecture, when we try to create the node, we're just like, the moment we create the node, we also create its children. We just create all the way down to the bottom, until the leaf nodes. But in this case, because you can have up to 10 to the power of 9 different values, it's going to MLE. So the concept of the lazy create segment tree is that because of other limitations within the questions, you're not gonna use all 10 to the power of 9 values. So the idea is that you have a separate function called create, and you only create your child nodes if you actually need them. So basically, for this one, don't ignore, ignore it for the moment. This is for lazy updating, which is you don't need this for this question, but it's for the other questions. But you can just ignore it for the moment. So basically we need to check if, because we have pointers that point to our child nodes. So basically L and R. When we don't create our nodes, these pointers basically point to nothing, which is basically this null PTR. So before we do anything, we need to check if it's equals to null PTR, and then if there's no children there, we need to create children first before we do anything. Otherwise, your program is going to crash. So this is actually quite simple. Basically, before you do any queries or updates, you just check if there's children, and then if there's no children, you just create the children. So what this does is that you only create the children when you need them, when you really need them, instead of creating them all at once when you create the segment tree. So this can help like cut down on this can prevent you from like creating nodes that you don't actually need. So it stops you from wasting memory, and it allows you to actually pass the question without MLE. Yeah, so that's basically it. That's basically it for question 2. Okay, yeah, so like this is like another solution. Okay, so question 3, ball games. We basically sort the students by their height. So basically the question is trying to say that we can only pass the ball to a we can only pass the ball to within a range of D, and then we can only pass the ball to a student with a shorter height than the current student. So let DPI be the number of ways to pass the ball from person I to the shortest person. So DPI is basically the sum of DPJ where J is less than where J, where J is less than I, and then the position the position is within range. So basically, because we can also think of it as this, so we have our J, and then we have our current student minus D, and then current student minus plus D. So that's the entire range that we can pass to. So we can basically use a Fenwick or segment tree to find a range sum, so that we know who to we basically in a way like to do fast range sums, because we are going to have to like sum up the things very frequently. So we can use a Fenwick or segment tree to actually speed up our range sums to calculate this much faster. Right, okay, so moving on to question 4. Question 4 is basically asking you to implement range update point queries. So the main idea is that basically because we learned about point update range query Fenwicks in our DS2 Fenwick lecture, so we can actually modify it a bit to allow us to turn it into a range update point query Fenwick, so that the idea is that instead of storing the sum, we store the difference. So let's say we want to increment 3 from index 2 to 5. We'll just add 3 to our difference array at index 2, and then subtract 2 from our difference array at index 6, so that for point queries we'll just sum up all the differences to get to the sum of the point. So let's say like all our values are 0 at first, and then we add 3 from index 2 to 5. So like let's say if I want to query the value of index 4, I'll just sum up the differences from index 1 to index 4. So that includes the 3 that we added to our difference array at index 2. So the sum of the differences will be 2. So which is indeed what happens, which is indeed what we want, because we incremented 3 from index 2 to 5. But let's say we want to query index 7. It's currently 0 because we didn't do anything to it. So we'll basically sum up the differences. We added 3 at index 2, and then we subtract 3 at index 6. So basically these cancel out, and 3 minus 3 is 0. So it will give us the value of 0, which is indeed what the value of index 7 is. So basically that's how to turn a PURQ into a RUPQ. So that's how we implement it. So here's a code for the implementation. Yeah, basically, but since because of the way the question works, when you add something, it adds all the way from that position all the way to the end of the array. So So like in this case, we only have like a s value. We only have a start, and then because the end is always at the end of the array, so all the way at the end where it's already, like if we try to add, it's already out of bounds. So we just simplify this to only have s to the end of the array, and then you increment v. Yes, so that's basically it for question 4. Alright, do you have any questions for the editorial?